Hello, my name is Magnus Petersen. This is my tutorial number 17 on TensorFlow, and this is about the Estimator API. The Google developers have made several tutorials on this topic already. This is the official one on the TensorFlow website. There are some inconsistencies between this tutorial and the contents of the source code, so this is actually somewhat confusing. This is a blog post by one of the Google developers, and this is actually not bad. It shows how everything fits together and how to use it on a dataset here. And it has a link to another tutorial up here. And this one I was not so happy with. This was not completely polished. So you have a lot of comments in the beginning, but as you get further down in the notebook, there are fewer and fewer comments. And there's also some of the Python code which is not very Pythonic. They have also written this paper, and I'm not exactly sure why they have spent time on this. I'm probably the only person who has read this paper. And you see, I mark sections of the papers that I read, so I can easily reread them again at a later date, like so. I think that they should have focused their effort on making the official tutorial better, instead of making 3 or 4 different ones, each of which has some problems. Now, I'm not sure that my tutorial is any better, but we can give it a try, and one thing is for certain, I will criticize the API, because it has problems, and you will not see this in the official tutorials from the Google developers. And I have gotten a lot of comments on my criticism of TensorFlow, the API, and so forth. And my philosophy on this is that I criticize upwards in the hierarchy. You would not see me attack somebody who was, for example, a student. But Google engineers are considered to be the world's elite, and so I think they deserve to be called out when they don't do a very good job. Especially because the community is also investing a lot of time and effort into TensorFlow. So I think the Google developers who are being paid big dollars by Google really should do a better job. So let's have a look. Now, I've said before that high-level APIs are extremely important, and this goes for software development in general, and that is because it provides high-level abstractions for doing very complicated tasks that you may have to do many times. So instead of writing, for example, 100 lines of code for each project that you're doing, you might have only 1 or 2 or 3 function calls to a more advanced API. And this makes it a lot easier to write and understand your source code, and it also dramatically lowers the risk of errors. So I am a big fan of high-level APIs. They are an absolute necessity in software engineering. And in tutorial number 3, we saw how to use various builder APIs for creating neural networks in TensorFlow, but there was still a lot of additional code that we had to write to do the optimization and loop over data and things like that. And the Estimator API is supposed to take care of most of this. And using the API consists of several steps. First, we have to define input functions for inputting data to the estimator, and we will see examples of that below. Then we can either decide to use an existing estimator, for example, for a deep neural network, and this is also called a Premade or a canned estimator. Or you can create your own estimator in which you would, for example, make a convolutional neural network, which we will show how to do below. And then you also need to define the optimizer and performance metrics and so on. And then you call a simple function to train the estimator using the data that you had defined in step 1. And then you can evaluate the performance of the estimator on the test set. And again, this will use the test set function that we defined in step 1 here. And then we can use the trained estimator to make predictions on new data that we haven't seen before. So, as usual, we have some imports. We need TensorFlow and NumPy and Matplotlib. And I get a warning here, and I think it's because there's an inconsistency between Python 3.6 and 3.5, somewhere in the TensorFlow.python.framework and so forth. It seems to be working all right, but there's this warning. I don't know exactly why. And I just upgraded to TensorFlow version 1.4.0. And we have already seen in many of the past tutorials how we load the MNIST dataset, so I'll just go over that very quickly. The labels for each of the images in the dataset is a one-hot encoded array like this. So the index of the 1 is index 7 in this array here. And in the next one, it is index 3 and index 4. So this means that the class for the first image is 7, and it is 3 for the second image and 4 for the next image, and so forth. And here we just get out the class numbers as integers as well, because we're going to need that. And here we define the data dimensions, which is useful so we don't have to use integers all the way through the source code. This makes it very easy to change if you want to use another dataset. And here we have the usual helper function for plotting images. And we can plot a few of the images in the dataset just to see that everything looks correct. So now we get to the point where we have to define our input functions, and these are responsible for getting data either from disk or from memory into the estimator. A lot of this code would be the same or almost the same across many projects. So having these APIs will help us to do this more easily, and it is more flexible because we can use data from many different sources and decide how it should be shuffled and various other aspects. And in our case, we have NumPy data that has already been loaded into memory. So the input function for the training set is created using this one, tf.estimator.inputs.numpy input function. And we have to define x and y, so this is the input and the output. Here we have x as the input images from our training set, and we have y are the class numbers for each of those images as integers. And this is important because we are going to use a premade or a canned classifier called DNN classifier, which assumes that the class numbers are integers. If we set the number of epochs to none, it means that we can read as much data as we want from this input function. And we set the shuffle to true, which means that the data will be randomized. There are more parameters, such as the batch size that is being returned, and the queue capacity, and the number of threads for reading and processing the input data. But you should read the docs to see exactly what these will do. So note that the train input function is actually a function, as we can see here. And if we call it, it will return a tuple that corresponds to the input data x and the output data y, as we have defined up here. And these are TensorFlow operations called random shuffle queue, dequeue many. So these are for getting data into a TensorFlow graph. We also need to create a similar function for the test set, and it's basically the same, except we use the images and the class numbers from the test set. And now we only want to run through this data set once, so we set number of epochs 1, and we don't want to shuffle it. There's no need to do that. If you want to use the estimator after it has been trained to predict the class number for some new, previously unseen images, we also need an input function for that. In this case, we will just hack it a little and use a few images from the test set. So we take those images here and we create a new input function. Note that this one doesn't need the y. It doesn't need the output because we are going to predict that. However, for plotting the images further below, we still need to know the class numbers so we can see if the prediction was correct or not. So we also just get the class numbers in this line here. So now let's try and use a premade or canned estimator. When I first heard about this, I thought the idea was to have models like, for example, the Inception model as a canned estimator, so you could easily load and reuse that, and other similar models. That is apparently not the purpose. The purpose is, as we will see in this example, to have a general estimator for fully connected deep neural networks, as an example. So let's try that. First, we have to define features. These are the input features. And this is not being used when you make your own estimator, as we will see below. And this is confusing, inconsistent, and I'm not sure it's necessary if they were to change the implementation of the premade estimator. It seems that it wouldn't be necessary. And it is inconsistencies like this that are some of the things I don't like about the Estimator API. So we have to make feature x for our input images, and it is tf.featureColumn.numeric column. Maybe this could have been shortened, so it was just tf.feature.numeric. So we didn't have to write this column all the way, and especially 2 times. Maybe it could do with a bit more polishing. Anyway, we have to give it a name, which we just say x, and we have to tell what shape it is. So this is the array shape of the NumPy arrays for the images. And then if we have more than one feature, we gather them together in a list so we can input them all to the estimator. And we want to make a 3-layer neural network with 512 units in the first layer, 256 in the second, and 128 in the last. Now we're ready to make the estimator, and we do that like this. So call tf.estimator.dnn classifier with the feature columns and the number of hidden units, and we decide that we want the activation function to be ReLU and the number of output classes, and then the directory on the disk where we want to save the checkpoints. And now that we have the estimator as an object, we can call functions on it, and we call train with the input function that we defined above for the training data, and we want to perform 2000 iterations. And it will save the checkpoint at the end and at intervals during the training. And now that the model has been trained, we can evaluate its performance by just calling model.evaluate. Now we take it on the input function for the test set, and you will note that it is reloading the parameters from the checkpoint that was just saved. Then it performs the evaluation, and the result is that the classification accuracy on the test set is 97.27%. We can also use the estimator to make predictions on new data. And remember from above that we had just hacked this a bit by using some images from the test set, but you could use whatever images that you would like. So now we call model.predict with the input function for these images, and the predictions are returned as an iterator. And when we go through that, you will notice that the checkpoint for the model is reloaded. So every time you call predict, it will reload the checkpoint from disk and recreate the TensorFlow model. And I suppose that if the model is really large, maybe like the Inception model or even larger, then this might be a significant overhead. It might take a lot of computation time to do this, and a better way would probably have been to keep the model and the checkpoint in memory so it was ready to do the prediction immediately. And if the checkpoint on disk had changed, then reload the checkpoint. There might be a technical reason for not doing this, but it's not explained anywhere. So until somebody clarifies that technical reason, I think that this is another design blunder for the Estimator API. And we have to do a bit of manipulations on the data that we get out. And I would encourage you to maybe make some more print statements here if you want to see exactly what is the data that is being output and that we are iterating over and so forth. But what we get out for those images are the class numbers that have been predicted. And we can plot that like so. For these 9 images, which are basically just the first images in the test set, the classifications appear to have been correct, all of them. Normally, I would show you incorrect classifications, but I have left that as an exercise at the end of this notebook. So now let's say that you are not happy with a deep, fully connected neural network. You want to create your own, and there's no pre-made or canned estimator that exactly fits what you want to do. So you need to make your own. And the way this has been done in the Estimator API is that we need to create this model function here, and it basically does 5 things. We need to define the TensorFlow model, for example, a convolutional neural network, and we have seen that in several of the previous tutorials how to do that. And then we need to specify what is the output of the model, and we need to make a loss function so that we can optimize all the weights and variables in the model so that it becomes better at classifying images from the dataset. Then we need to define the optimization method that we want to use, and if we want any performance metrics as well. In this case, we want to know the classification accuracy. The estimator can be run in 3 modes: training, evaluation, or prediction. And the code for this function is mostly the same, but it is slightly simpler in the evaluation mode. And this model function, which I'm about to show you, I think it's a bit like ANSI C programming back in the old days, where you would make structs and pass them around. I don't think it's very elegant, and it's a bit messy because it takes and combines many different things into one function. I think it would have been better if we had to subclass the estimator class, and then we would have to override functions to define various aspects of the model and the optimization method and so on. I think that would have been a more elegant way of doing this, instead of cramming everything together in a single function. So we have this one, which is being called by the Estimator API, and we will see that further below as well. So we get the features in, and this would be the X argument from the input function, and we will get labels in. This is a Y argument from the input function, and you can see the input functions that we created above for examples of this. And then we have the mode, which is either train, evaluate, or predict. And then we can also have some user-defined parameters, and in our case, we will use the learning rate for the optimizer. So first we need to get out the feature with the name X, and I just make another variable, also call it X. This is a 2-rank tensor, and when we have convolutional layers, we need to reshape it so it's a 4-rank tensor. So they are images with width, height, number of channels, and then the batch number here. And then we create the first convolutional layer with max pooling, and you should see tutorial 2 and 3 probably for more details on how this works and what it all means. And then we can create the second convolutional layer, and then we will flatten it to a 2-rank tensor. And once again, this has still not been implemented, and it's getting quite a... I actually think this is it's silly. It's funny and silly and annoying at the same time. You get really pissed off about things like this, and then you reach a point where you just laugh at it and think, whatever, this is just ridiculous. And they actually closed the issue that I had made on GitHub and said I had to make a pull request for this. Absolutely not. This is your code, Google developers. If you make a mess, you clean it up. You get paid for it. I don't. And then we add some fully connected or dense layers, one here and another one. And this is actually the final layer, which we also call the logits. And we will do a softmax on that so we can get the predicted class out. And again, you should see tutorial 2 and 3, I think, if you are not familiar with this. And then we have to switch. As I recall, I made this code quite a while ago and I had to do some traveling in Eastern Europe. And now I've gone back to it, but I think this was more messy in the original tutorials. I cleaned it up a little. Let's have a look. Yeah, so this is a model function for the official tutorial, and this is actually really bad coding style. This is, I don't know why Google hires engineers who code like this. This is bad. You are not supposed to return in this fashion. You can do it in very simple functions, but it is way better that you return at the end, because then you can easily follow the control flow of the function. This is much harder to understand and debug. Yeah, this is bad. Because then it continues over here, and then it has another return down here. So like I said, I cleaned this up a bit. If we are in the prediction mode, we have to create the so-called estimator spec, and this is equivalent to the anti-C struct, more or less, where we once again have to set the mode, whether it's train or predict or whatever, and then we have to set the output of the model that we have just created in TensorFlow. So this one here, which is the output of this convolutional neural network that we have created. If the mode is not prediction, then it is either training or evaluation, and then we need to define the loss function that is going to be optimized, and we do that as usual by using the cross entropy, and again you should see one of the previous tutorials for that. Here we have the labels as integers, so we have to use sparse softmax, cross entropy with logits. If you're using one-hot encoded arrays, you would just change this by deleting this sparse here, I believe. And that's an exercise, and you can see if you can get that working. And this calculates the cross entropy for each of the images in the data batch. So to get a single scalar value that we can optimize, we need to reduce it by taking the average. Then we define the optimizer that we want to use, and we get a TensorFlow operation for performing a single step of minimization using this loss function. And then we just have the global step counter so that we can count it. We then have to define all the metrics that we want to use, and in our case it is just the classification accuracy. And once again we have to wrap this in an estimator spec, which is again basically just like a struct in the C language, which is not very elegant, and then we return the spec. And now this function only has a single return statement at the end, so the control flow of this function is very easy to understand. Well, fairly easy to understand. It's still a bit messy, like I keep saying, but it's certainly better than what they have done in the official tutorial where they would return the spec already here. And yeah, that is just ugly and dangerous coding. Don't do it. Alright, so now we have to make an instance of the estimator, and first we define the parameters that we want to use, and we just had the learning rate, and this is pulled out again up here in the model function where we create the optimizer right here. And this model function is then passed to the estimator class, and it will call this function whenever it needs to recreate the model. And you can insert print statements into the model function, and you will see that it is called every time, for example, we call the prediction. So if you have a very large model that takes a fair amount of time to create for the TensorFlow graph, then that would be called every time that you want to continue training or testing or doing a prediction on new data. But anyway, this returns the estimator object, and then we will just call it like we did before with the canned estimator object. So we call model.train, and then we take the same input function that we had defined above, and in this case we just perform 2000 steps again. And once that is done, it will save a checkpoint, and it should also do this at regular intervals. And then we can use this trained model on the test set, and we get a classification accuracy of 97.61%. We can also use the trained model to do predictions on new data, and we just use the hacked input function from above again, and we get these predicted class numbers for those images, and we can show them here, and once again it appears that all of them are correct. So these are the basics of how to use the Estimator API. And the intention is to make it easier and safer to train and use your model. But I'm not completely sold on it. I think the API is too complicated. I think it's inconsistent and confusing. For example, that you have to define feature columns for canned estimators, but not for new estimators that you make yourself. Why is that? That's not obvious. The model function is also a mess. Even worse, the error messages are extremely long and often they are almost or really completely impossible to understand, and you sort of have to guess what is wrong with your code because of this calling back and forth between the Estimator API and, for example, the model function. Another issue is that the TensorFlow graph is recreated and the checkpoint is reloaded every time you want to use a trained model to make a prediction on new data. And if the model is very big and you need to have a very high throughput of data, then this is a problem. And a better way would have been to simply only reload the checkpoint if it has changed on the disk. Maybe there's a technical reason why they haven't done this, but it's not explained. So again, I think it's a design blunder. Furthermore, it is unclear how to gain access to the trained model. I think you can probably load the graph from disk, load the checkpoint from disk, and then use some of the code from some of the previous tutorials to do that. It's an exercise. You can try and figure out how to do this, but this would probably be a lot easier if the estimator didn't throw the graph away every time it had been used, but it just kept it in memory. Then we could gain access to it more easily. So I think the Estimator API could have been made much more simple, and you may find that if you're just doing small projects or if you're doing training that is very unusual in some way, then the Estimator API may not be for you. I think it gets easier. Certainly I feel it's getting easier as you get more experience with it. And it's also possible that if you work with really large data sets or you use many machines, that it may make it a lot easier for you, even though it is not the best and most clean and simple API that it could have been and should have been. So as usual, you can download all of this source code by clicking on the link below the video.